In this next subsection, we're going to look further into these autoregressive models. We're going to explore some of the details behind them. But first, let's think about how perhaps one would have approached modeling time series data prior to this particular course. So let's say we have some time series x of t, and what one would have maybe done is take a regular old regression model, x of t is equal to beta 0 plus beta 1 times t for time, plus epsilon sub t, where epsilon sub t is distributed independent normal 0 sigma squared. So could one use this kind of model for time series data? And the answer is yes. But the problem, though, is with this is that your inferences might be incorrect, meaning that your confidence levels for any kind of inference will be off. Your type 1 error rates will be off, and so that's why this approach is not done. And why are these off? Well, it's because we have this dependence in our data, which is not being accounted for by the model itself. Now, you might think, well, maybe there is some set of explanatory variables that might help detrend a response variable so that perhaps just white noise is left over, and so that epsilon assumption here actually works. And in the end, this is very often not possible. Later in this course, though, we will talk about using regression models like this, but we will not use independent normal 0 sigma squared for our epsilon term. We will use something else. Instead, what we're going to use are autoregressive integrated moving average models, or ARIMA models for short. These models were developed for time series data by two guys named Box and Jenkins in the 1970s. These two individuals then have come up with a number of editions of a textbook corresponding to these methods that are essentially the standards for time series analysis. They are now both deceased, though, and other authors have then written subsequent editions of these books, so the name Box and Jenkins still ends up being on these corresponding textbooks. Okay, so with an ARIMA model, there are essentially three different parts. There's the AR part, the autoregressive part. There's the MA part, the moving average part, which is similar but not exactly the same as what we've seen previously for a moving average, but very similar. And then there is the I part, which stands for integrated. This is closely related to differencing, to eliminate non-stationarity in the mean. So in the end, we've essentially talked about all parts of an ARIMA model. Now in this section, we're going to put these parts together to have one overall modeling strategy to deal with time series data. Okay, so let's talk about these autoregressive models now in more detail. So the basic idea, we've seen an autoregressive one model before. Now we could have, instead of just one, let's say, term from the past, we could have two, we could have three, we could have up to, let's say, p different terms from the past or values from our series in the past, excuse me, where we're going to try to estimate what x of t is, our present value. So if we go back to, first of all, this AR1 model that we've seen before, this is what it looks like once again, where we have this, we go one time period in the past to get at what x of t is. Wt is our white noise in order to do some estimation, which we will talk about later in terms of trying to figure out, well, why should I have a 0.7 there maybe versus something else. We will make a normal distribution assumption associated with it. And so what this model basically says is that, again, x2 comes about through taking 0.7 times x1 plus w2. x3 comes about in the same way. Take 0.7 now times x2 plus w3. And we will have a whole subsection shortly on forecasting. And so if we observe up to, let's say, n different values for our time series, you're going to be typically very interested in, well, what's that next value, that n plus 1 value? And the way that we're going to do that is take 0.7 times x of n. More on that again later. So in general here, this is what the autoregressive model looks like up to p past time periods incorporated into it. So we have x of t is equal to, and then we have a parameter here, which is phi sub 1 or phi 1. It's going to be multiplied by x of t minus 1. So if you can imagine that if, let's say, phi 1 was actually 0, we can see that going one time period in the past is not going to help you get at what x of t is. If phi 1's positive, it says again there's a positive association with what was done one time period in the past. Similarly, if it's negative, it says that there's a negative association. But we could also have two time periods in the past, and we're going to have a parameter phi 2 associated with it. And we could keep on going all the way to p time periods in the past, and we have phi sub p. So you can see some relationships between this kind of a model to what we would have for, let's say, a regular old regression model as well. Then we end with our white noise. Now, some notes. Some textbooks will use a different form of phi to represent this parameter. There's actually two different ways to actually draw the phi, and I simply have chosen this particular way here. Now, to find parameter estimates, as I mentioned about a minute or two ago, we will make an assumption that rather than just plain old white noise, we do have a normal distribution corresponding to our white noise. Now, this next note is very, very important. Now, without loss of generality, we can assume that the mean of x of t, let's call it mu, is equal to 0 for our general model that we just displayed. However, mu is not going to be equal to 0 for most applications. Well, why do we make this assumption then? Well, very simply, if mu does not equal 0, all we would have to do is replace the x of t that's in our model right here with x of t minus mu. Now this would also be at time t minus 1 and t minus 2 and so on as well. And so if we did do that replacement, here's x of t minus mu is equal to phi 1 times x of t minus 1, that quantity minus mu, and we can keep on going here as well. Then we can do a little bit of algebra so that now we have what you can almost think of as, your beta 0 term in a regular old regression model, where it has all these, but it's actually a group of all these parameters all together. And how about we just call this simply alpha? Now we will want to estimate this alpha as well. Now, why though is our time series model when we typically represent it, and it's just not in my notes, but typically in other textbooks as well, why is it represented without this alpha in there? Well, remember with time series data, we're very concerned about the dependence over time. And a simple constant like this is going to have no effect on what the dependence is. That's like saying, well, what's the, let's say, correlation between a random variable x and a constant, we'll just call it beta. Well, that correlation is 0 because beta is a constant. It's not a random variable. And so again, since time series is so concerned about that dependence, that's why often this term gets dropped in the general representation of the model, but we cannot forget about it because we will want to estimate it. Perhaps I should just simply rewrite all my notes and always have that term in there. I've kind of debated about whether or not to do that. In the end, I've just decided to go with the formulation of my notes as I have now. So you might want to put in your notes, put a big star by this. We will, when we estimate this model, we will almost always include an estimate of alpha in the model itself. Okay, So we could also represent our model in a vector form as well. So x of t is equal to a vector, a p by 1 vector of these phis. Transpose times x of t minus 1, that's a p by 1 vector as well, corresponding to going back t different time points. Here's something else that's very important. When these kinds of models are represented, most often it's actually represented using our backshift notation that we've seen previously. So what we could do with our model, let me come back up here to this original model. Let me copy it and paste it. What we could do with this model, let me do a little erasing, is we can incorporate this backshift notation as x of t is equal to phi1 times b times xt plus phi2 times b squared times xt plus, and we can keep on going all the way down to the pth term here. And now we've incorporated our backshift notation. Notice how we have x of t represented in multiple places. And so what we're going to do, take all these x of t terms, bring them over to the left side of our equation, factor out xt, and here is how we can represent this model in a little bit more condensed form using our backshift notation. Notice here how now I have a negative because I brought it over to the left-hand side of my equation where it was on the right-hand side before. That's going to be important coming up. And we can even write it in a little bit more compact notation where this whole term here can be represented by what's called an autoregressive operator, or AR operator. Phi of b times x of t is equal to w sub t. Again, we will be using this notation throughout our course. Another very important aspect of this kind of model is that we can rewrite it so that we just have x of t on the left side. And on the right side, you can have just a linear combination of your wt's. Actually, it's going to be represented as an infinite sum. So we can re-express our model as a linear combination of the wt's by iterating backwards. Okay, what does this mean? Let's take a look at the simplest case with an AR1 model. So x of t is equal to phi sub x of t minus 1. I just decided to drop off the 1 off the phi since there's only one phi that we're going to be working with. And we have wt. And so what we can put in here in terms of our model, what is x of t minus 1? Well, it's phi times x of t minus 2 plus wt minus 1. And if you simplify that sum, notice we still have an x of t on that right side, but now we have two of these w's. Then we can plug in, well, what is wt minus 2? Do a little bit of algebra, and this is what we get. Now we have 3 of these w's on the right side. And you keep on going and going and going until we get to a point that looks like this, where now x of t is written as the sum from j equals 0 to positive infinity of phi raised to the j power times w sub t minus j. And this is all because this is all relying on that the absolute value of phi is less 1. Otherwise, you're going to have a non-finite series. To understand that a little bit more in a little bit, I guess, a better mathematical way, how about we rewrite our model like this? So that now we have 1 minus phi times b, that quantity times x of t is equal to wt. And we can simply bring this part here over to the right side like that. Now, this stuff that we have on the right side in front of the wt should look somewhat familiar. back in at least like a Calc 2 class, and probably even before in an algebra class, you should have learned about the sum of an infinite series, what happens with it. So if I have 1 over 1 minus a, where the absolute value of a is less than 1, then I can rewrite this as the sum from I equals 0 to infinity a raised to the ith power. We're going to do exactly the same thing here. This phi times b is basically going to play the role of our a. And so that now, then, we can take that 1 over 1 minus phi times b and write it as this infinite series. Then we can say, okay, this is now a little bit more compact. The sum j equals 0 to infinity, phi raised to the j power, b raised to the j power times wt. I can bring that backshift notation into the w itself, and so I have w sub t minus j. So what we've done here is we've rewritten our autoregressive model now as a infinite sum of these w's. This is going to be very useful for our work, and you'll actually see why in this next bullet too. Okay. Now, let's talk about the mean and autocovariance function for an AR1 stationary model. And we're going to use this infinite sum way of writing our model. So the expected value of x of t is equal to the expected value of this infinite sum. I can move the expectation inside the summation. The phi part there is just constant, so I can further move that expected value in. And of course, each of these expected values of these w t minus j's is equal to 0. So the expected value of t is equal to 0. What about the autocovariance function now? So gamma of h is equal to the covariance of x of t and x of t plus h. I can rewrite that out in terms of my expected values. Each of these expected values there are equal to 0, so I'm left with just the expected value of x of t and x times x of t plus h. Okay. Now I can take each of these x of t's here and rewrite them in terms of this infinite sum of the w's. So that's what I do. We'll call that, let's say, maybe step 1. Step 2, so that I can see things a little bit better, I'm going to actually write out what that infinite sum is going to look like. And then, similar to what we've done before, let's say step 3, I look at specific cases corresponding to what h, that lag difference is. Now, if h is equal to 0, of course, then we simply this term and this term inside the expected value are exactly the same thing. So that's why I have a squared there now. And then I use the what we've actually done before, and that is, of course, if I had, let's say, the variance of a random variable y, this is equal to the expected value of y squared plus expected value y, that quantity squared. I can take this, move it over to the I'm sorry, I don't want to do that. I can take this part here, move it over to the left side, and so I'm just left with expected value of y squared on the right side. And so this is what I do here. I just have a little bit more complicated term. So I have the variance of my infinite sum plus the expected value of that infinite sum, that quantity squared. We know, excuse me, we know what this expected value is. It's equal to 0. With respect to this variance here, I have a variance of a linear combination of independent random variables. So I can bring that variance inside the sum. Any constants get factored out and they're squared. And so that's why I have the sum from j equals 0 to infinity of phi raised to the 2 times j power times the variance of w sub t minus j. We know what that variance is. It's sigma squared w. And so we're left with then sigma squared w times the sum j equals 0 to infinity of phi raised to the 2 times j power. Now, again, as long as phi is between -1 and +1, we have the sum of an infinite series working here. And so we can take this sum, and it ends up being 1 over 1 minus phi squared. Now, a little bit of a side note, I'm going to eventually get to this as well. We will have particular constraints that we work with in terms of these phi parameters with our autoregressive models. So making this assumption here with the absolute value of phi being less than 1 is something that we will actually be doing throughout this entire course. Okay, so we have found the autocovariance at lag 0, which of course then would be the corresponding variance. Next, let's take a look at what happens when we have h equal 1. So in my expression for my autocovariance with this expected value, I'm going to, wherever I saw an h before, I'm going to replace it with +1. Now we can have some simplifications that occur here. Notice the area that I'm going to highlight. That's exactly the same as what I have up there, except for I have an extra phi to work with. So what I can do then is take wt plus 1 multiplied by this first stuff that's in the parentheses, and that's what I do right here. Then, let me do a little bit of erasing. Then, how about I factor the phi out of the rest of that infinite sum? And so then what I'm left with then is I have exactly the same infinite sum, so then I have a squared there, same as what was up here, but I also have that extra phi to work with. Okay. Now, let me do a little bit more erasing. Okay, so let's take a look at this first set of terms here. Notice none of the subscripts match up. So this wt plus 1 then is, you can think of that, treat that as separate from the stuff that's in the corresponding parentheses because of independence. So now I can bring that expectation through, and I know that this expected value is equal to 0. So then that greatly simplifies what I need to find. And I can spend my time now concentrating on the second term that's inside this expected value. So phi is a constant. I can factor that out of the expected value. And then what I'm left with then is essentially what we had previously for h is equal to 0. So I have a phi times exactly what I had before at actually at h equals 0. So then, in the end, when h is equal to 1, here's my autocovariance. Exactly the same as what it was for h equals 0, but now I have this extra phi. And in general, you could keep on going, and you're going to find a patterns that form, and gamma of h is going to be equal to phi raised to the h power times that sigma squared w over 1 minus phi squared. So then this leads this into the autocovariance function. So I could simply take this term divided by sigma squared w over 1 minus phi squared. Things are going to cancel out here, and I'm left with just phi raised to the h power. That's the autocovariance function in general for this AR1 model. Now, one could come about doing this little proof in a little bit of a different way, going back to the results that we've seen before relative to a linear process. So just to review, we saw a linear process defined like this. Notice how it's written as an infinite sum of these w's. but it goes down to j equal to negative infinity up to j equal to positive infinity. Well, for us, we could assume that each of these psi sub j's, when I have a negative subscript for them, I can assume all those are equal to 0, and then take advantage then of the final result of what that autocovariance function would be, and write it out, and there's your autocovariance. The key, though, is that you'll need to figure out, well, what should be these psi's in terms of our model itself. So what are these psi's? Well, we can go back to what our original model gave us, and I have already, here's a copy and paste of our original model, and we can easily see then that this, for example, this psi sub 0 would be equal to 1, psi sub 1 would be then the phi, psi sub 2 would be phi squared, and so on. So using that result then, we can simply plug that back into our expression for the autocovariance function. Make sure you can go through the details on your own and get exactly the same as what we had before. Okay. Now on your own, I want you to also think about the following questions. What if mu does not equal 0? How is that going to affect some of our derivations that we just did here? I kind of gave the answer about 5 or 10 minutes ago, but I still want you to think about how that's going to affect everything. Will this cause the expected value of t to change? Will this cause then gamma of h to change? Okay, so let's get into an example here where we start working with some data values. So we're going to look closer into this AR1 model where phi is equal to positive 0.7 as we've seen before. But also what happens if phi is equal to negative 0.7. And we're going to work with a case where sigma squared w is equal to 100 as well. And we have n is equal to 100. We're going to look at some plots. When you look at these plots, think about, well, what makes some of these plots, let's say, more jagged, or maybe things are oscillating more in these time series plots, that is. How does that relate to what these particular values of phi are? Think in terms of what that autocovariance function has given us. And also, what would happen if, let's say, these values of phi were actually closer to 0? What would happen to the plot over time? Remember throughout that the autocovariance function, its autocorrelation function, is equal to phi raised to the h power. So what that means then, at let's say lag 1, I have a positive correlation of 0.7 when phi is equal to positive 0.7, and when phi is equal to negative 0.7, now I have similarly a negative autocorrelation. But also then look at what happens through different lags. When phi is positive, I still have this positive dependence that occurs. When phi is negative, look what happens. At lag 2, now I have a positive autocorrelation. At lag 3, now I have a negative autocorrelation. Now just think about right now, before we take a look at these plots, what would you expect these plots to be over time? So here's a plot now for the model where phi is positive. And we've seen a plot like this actually before. And what we can see is that we have, for let's say small values of h, we tend to have general agreement about what these values of x of t are. And so because of that, we're going to have, let's say, maybe slower oscillation of these of the time series over time. You're going to have some values that look like this, where we tend to be right about the same level over a larger period of time because of this positive autocorrelation that we have for the different h's. But then when we have a negative value there, look what ends up happening. Remember that rho of 1 is now going to be negative 0.7. So we have an inverse relationship that's happening here. In terms of if I have a high x of t, I would expect to maybe have a low x of t minus 1 when I'm separated again by that 1 lag. And look what happens on this plot. Take a look at this point here. Take a look at this point here, separated by 1 lag, and we see exactly what I had been saying, that we have this this negative dependence between the 2 lags. But we also know that rho of 2 is equal to a positive 0.49. So when I'm separated by by a lag of 2, I would expect, generally speaking, to have similar values. So for example, take a look at those 2 points right there. And so we see a lot more higher oscillation throughout this plot when I had a negative value for my phi. Now again, think about what would happen with these plots if, let's say, phi was, larger in absolute value or smaller than in absolute value. In fact, you can take a look at my corresponding program, which is AR1_sim, and actually simulate the data, which I will actually show you how to do shortly, and plug in different values of phi to see what would happen. Okay, so let's talk about how we can simulate data from this R01 model. We've talked about this a little bit before using a for loop. Here's a much simpler way to do this. So to do it, I'm going to set a seed so I can reproduce my results. Excuse me. And to simulate my x, I'm going to use a function called ARIMA.sim. In the first argument here, model, this is where I can list out what my phi parameters are, depending upon the order of my autoregressive model. So let me actually come over here to 10 to do this. And the way that I list out my corresponding parameters is I use a function R called list. So I'm actually going to create a list to do this. And I need to specify, okay, for my first component of my list, these are going to be my AR parameters. And I only have one parameter, so I can simply write out 0.7. If I had more than one, I would need to combine together the AR parameters using the C function, the concatenate function. In this case, again, I'm just going to use one, and so I can still use the C function with this if I wanted to. It's not going to make a difference. Then I'm going to simulate 100 values. I want my my white noise term to correspond to a normal distribution, so I'm going to use the rnorm function to do that. This is then when I can also specify particular argument values for rnorm, and I'm going to specify my standard deviation to be 10. I'm going to go with the default for rnorm for the mean of 0. Now, why can I do this? Well, if you look at the corresponding help for ARIMA.sim, you will notice that there's a ... part to the function call. And what that does, if you haven't encountered that before, it allows you to pass in additional argument values that are not necessarily in the function itself. These additional argument values then are try to be matched up to other functions that perhaps then this ARIMA.sim function actually relies upon. If you have questions about that, you haven't encountered that before, just let me know and ask me. I'll be happy to explain that more. So if I go ahead and simulate that data, I can type in X there. There's my simulated time series itself. Notice it is a TS type of class for the object. And I can use then the plot function using similar methods to what we've done before to plot then the corresponding data. And I will get this particular plot there. Okay. Excuse me. Now here's something you got to be very careful about, and that's why I've highlighted this. Excuse me again. Now, notice I put a positive 0.7 value in there. If I were to write out my model like this, x of t is equal to 0.7 times x of t minus 1 plus wt, of course it makes sense to put in a positive value for that phi parameter. However, if instead I would have wrote my model out like this, let me change that. You might be thinking, oh, wait a second, shouldn't that be a negative value? And the answer is no. Even though I'm using this autoregressive operator kind of way to write out my model, you ignore that negative out there because that's just how we typically define our model. And so actually it's a positive 0.7. This can be very confusing to people who are new to time series. In fact, some textbooks, the way that they will define the autoregressive operator is so that it will actually have a positive there instead. And so now you have kind of the reverse then when you rewrite the model so that then like x of t minus 1 is on the right hand side. So you got to be very careful. You have to understand how R defines what you're putting in there for that parameter value. And again, just be very careful. So now if I were to, let's say, want to simulate data from this AR1 where I had a that negative 0.7 for my model, so I can simulate this particular data right there. Notice how when I write the model, so I only have x of t on the left-hand side, I now have a negative there. I would then put a negative 0.7 in there for that AR component of my list. Even though when I write the model in terms of like this where I have the AR operator on the left-hand side, actually I see a positive 0.7. Okay. So I've already talked about that if you had, let's say, more than one phi parameter. So we've talked about how to derive the autocorrelation function ourselves for an AR model. Well, R has a nice little function called ARIMA ACF that for specific numerical values for your phi will do this automatically for you. So let's talk about how we can use this particular function. Okay, so let's see here. So again, there's the function itself. And it's actually fairly easy to use. Let me just come on over here to 10 to do this. And I can say ARIMA ACF, first argument is AR, and I plug in what my corresponding phis would be. If I had more than one phi, I would have to concatenate them together. In this case, I only have one. I can specify, well, how many lags do I want to go up to for this corresponding autocorrelation function. And just to make things look a little bit nicer, I'm going to go ahead and round everything to 4 digits. And here we go. Again, ignore lag 0 because that will always be 1. But at lag 1, we see we have a value of phi, 0.7. Now at lag 2, remember that autocorrelation function is phi squared. Well, look at this. We get 0.49, 0.7 squared. Lag 3, 0.7 cubed, 0.34, and so on. Now we can go ahead and do a plot of the autocorrelation function as well using the plot function. And let me bring that over here. And here's what it looks like. And let me actually show this in Word so I can nicely write on it. And so once again, we have the lag 0 value, which is not important to us. Here's 0.7, here's 0.49, and so on. So we can see with an AR1 that the autocorrelation decreases through the lags. And we've kind of discussed this in the past and why that should make sense. That, you know, once you're at time period, let's say 10, right here, with an AR1, when you're only using x of t minus 1 to get at x of t, it makes sense for 10 time periods in the past to not have much of an effect at all on what the current value is. Now, something that you got to be careful about when you do this kind of corresponding plot. Now, notice I use a y argument to say, let's put these autocorrelations on the y-axis. On the x-axis, I put in 0, 20, which means 0, 1, 2, all the way up to 20. Why? Well, because that's where this ARIMA ACF function, that's where it starts for the corresponding lags. It starts at h equals 0, and it goes to h equal 1, and so on. Now, to do this particular plot, I also did something we haven't seen before. I use a type argument that has a value of h. I think of the value h as the word high, as in how high do you want to draw the points from the 0 line corresponding to the y-axis. So if I page up here a little bit, notice I'm 0.7 there for lag 1. So what this argument says, okay, let's start at 0, and I'm going to draw a line all the way up to 0.7. If I had a negative autocorrelation, instead it will maybe draw a line starting here and go down. So that's what this type argument does. And in fact, if you run the same code with phi1 equal to negative 0.7, you see again, everything's drawn from the y-axis value of 0 on the plot. Now you got to be careful though when you use the results from ARIMA ACF when you do this plot. If instead I would have done this, suppose I didn't put a y argument at all in there, and we've seen this when we've done one of these plots of our data over time, a time series plot. Suppose I just put in x equal ARIMA ACF and had everything else there but that y argument. Well, R is going to produce a plot, but the problem is it doesn't know that the ARIMA ACF function starts at lag equals 0, and instead this is actually lag equal 1. We have 2, we have 3, we have 4 there. So essentially this plot, the x-axis is shifted 1 to the right, and it shouldn't be. So be very careful when you use the plot function. Okay, so let's take a look at another example dealing with an AR1. What if phi1 is equal to 1? Now previously we've had phi1, the absolute value that has to be less than 1 when we were doing some of our derivations. The purpose of this demonstration here, is to help show you what happens if phi is actually equal to positive 1, and in fact if it was even greater than 1, similar things are going to happen. And so what this is going to lead to is a brief discussion about, once again, how we have constraints on our phis for an autoregressive P model. We will see what these constraints are specifically later on in another subsection. But I think it's good to bring this up right now so you start thinking about what the consequences could be if you're outside of what these constraints give us. So what I did here, and I don't have a program corresponding to this, but you could use a for loop to do this in a similar manner to what we've done in the past. I put in phi1 is equal to 1, and I simulated the data. And so what we can see here is that we have non-stationarity in the mean. That mean appears to be changing throughout time, where time's on the x-axis, x of t is on the y-axis. So therefore we have a non-stationary process. Here's another example from exactly the same model as well. We see that the mean appears to be changing over time. Try some more on your own to see the effects of what if you are actually outside of these constraints that we have set for our particular model. This then leads to a discussion of a causal process. Now, with an AR1 process, if, let's say, the absolute value of phi1 was greater than or equal to 1, this model can actually be rewritten in a way that is now stationary but future dependent. Meaning you might have something like this: x of t is equal to phi x of t plus 1 plus wt. In a time series context, that doesn't make sense. I'm going to use one time point in the future to predict what the current value is. So it's not useful at all. So when we have a process that's stationary and does not depend upon the future, we refer to the process or our model as causal. So you think of the word cause there to see where that name comes from. These are the kinds of time series models that we will be interested in. With these kinds of models, then, we can now rewrite our AR1 process as this linear combination of our infinite linear combination of our W's. So if you remember before, we said, okay, if that absolute value of that phi was less than 1, we now have then this infinite sum that we can use, using some results from like a calculus 2, an algebra class. We can actually come up with a nice form for this infinite sum. So we can also write then a higher order AR model, an ARP model, in terms of this infinite sum of these WTs as well. And this is very, very useful to understand how to do, so that we can start deriving autocovariance functions with these more complicated AR models. And so to examine this a little bit further, here's our general model for an ARP process or ARP model. I can write this in a convenient form using the autoregressive operator itself, and then I could then bring that phi of b over to the right hand side. So now I have 1 over phi of b times wt. How about we then say, okay, now I have a psi operator, psi of b, that's going to be equal to 1 over phi of b. This then helps me figure out what the individual psi terms would be, like what we saw with the linear process, what these individual psi terms would be, so we can nicely write the WTs out as a linear combination. So here's what the psi of b should be, and I should have brought this up before. It's just 1 plus b times psi of 1 plus b squared times psi of 2 plus so on, and it's an infinite sum. Okay, so if I say that 1 over phi of b is equal to psi of b, this then is equivalent to 1 is equal to phi of b times psi of b. And so what we have here are polynomials written in terms of these b's. And if we want to figure out then what these psi's would be in terms of the phis, then we can go back to our algebra days where one did something very similar to that, where you equate the powers of the b to what's on the left-hand side. So let's take a look at that, what I mean by that. So once again, I write out what I have here. 1 minus this operator dealing with the phis times the operator dealing with the psi's. And then I start multiplying stuff out. So to begin with here, I take this 1 and I multiply it times each of the individual terms for the psi of b, the AR operator. Then I take psi 1 times b. I multiply it by all the terms in the AR operator. And I keep on going here. Then I try to reorganize the stuff that's on this right-hand side So let's see, that's step 2, that's step 1. Step 3 here, I try to reorganize stuff that's on the right hand side so that I have the powers, I have all the corresponding terms for the same power of b. So for example here, I have 2 terms that have b raised to the 1 power. And so I take this down here and I get psi 1 minus phi 1. Let me erase. Oops. Then I look at all the b squared terms. Here's a b squared, here's a b squared, here's a b squared, here's my b squared now, and I have then the corresponding terms as a in that parentheses there as a coefficient on the b squared. Okay, so again, the purpose is to figure out what these psi's would be. So now I equate powers to what's on the left-hand side. And so you see I have a 1 here. This is like b to the 0 power. So I have a 1 here. This is like b to the 0 power as well. 1 is equal to 1. Now on my left-hand side, I don't have any terms that have b raised to the 1 power. So I take that to mean that I have a 0 times b to the 1 power. And so that means also psi sub 1 minus phi of 1, or phi sub 1, should be equal to 0. So psi of 1 now is equal to phi 1. For b squared, again, I don't have anything on the left-hand side of my expression, so I have 0 times b squared. So that's why I have a 0 there. But I do have some stuff for b squared on the right side. I have psi 2 minus psi 1 times phi 1 minus phi 2. If I go through the algebra, I get psi 2 is equal to phi 1 squared plus phi 2. I can do the same thing for the b cubed power, and I get psi 3 as shown here. And then you're going to have some simplifications that occur. You're going to see some patterns, so that psi j is equal to this expression here. Make sure you can go through that on your own to see that. Okay. So then for an AR2 process, what does that mean for us? Well, with an AR2, I would have 1 over 1 minus phi 1 times b minus phi 2 times b squared. So again, perhaps this is not needed, but I'm going to write it out. This is what my model would have looked like to begin with for an AR2. I just simply took this part here, brought it over to the right-hand side. And I want to now rewrite this so that it's this linear combination of the WT. So I need to find what the psi 1s would be. I'm sorry, what the psi's would be. So here's my infinite sum with the psi's. Here's my sum with the phis. And I can go through a very similar process. For some reason here, when I wrote up my notes, I decided to go about this way, where I take 1 times each of these terms right here, and that's what I get there. Then let me do some erasing. Next, what I do is I take this negative phi 1b times all the individual terms there, and this is what I get then in the second line, and I keep on going. When I equate the powers, what we see is that psi 1 is equal to phi 1, psi 2 is equal to phi 1 squared plus phi 2. I do the same thing for the third power as well. And in general, we get this nice expression for what the size should be. Make sure you can go through the details on your own. Now, if we think of a special case where we have an AR1 model, so that means phi 2 is equal to 0, look what happens. 0 goes into there, and now we have psi sub j is equal to just phi 1 raised to the j power. Now, to help us do this kind of stuff, and again, the reason why we want to do this, sorry if I'm repeating myself, is so that we can then derive autocovariances and autocorrelations, because each of these W's are independent of one another, and we saw how useful that was previously with just an AR1 model when we had our model written just in terms of the W's. To help us out to find what these psi should be, R has a function called ARIMA to MA, which in a general sense converts an ARIMA model to an MA model, a moving average model. We've seen a little bit before what a moving average model. We'll look at it more specifically shortly in a subsection of our notes. But what we can see here, if I page up, when I rewrite my model so that its x of t is equal to something times wt, that looks like what we saw before for a moving average model, where we just had this linear combination of wt's. And so that's why R has this function ARIMA to MA. And so let's look at how this works. So let's say I have an AR1 model with phi1 equal to 0.7. Then if I use the ARIMA to MA function, I have an argument called AR. I put in my 0.7 there. How many lags do I want to go up to? Let's say 20. What R then spits out is my size. So here is psi1, here is psi2, and so on. And based upon what we saw previously, that matches up. 0.7 to the 1 power is psi1, 0.7 to the 2 power is psi2, and so on. But you can imagine, as we saw actually for an AR2 model, that as that P increases, the order of the autoregressive, this gets to be a pain to have to do these kinds of derivations. And this function, when you have specific values for your phis set up, will find the numerical values for the size. So just to show you, here's what everything looks like then when I have an AR2 model where I have specific values for phi1 and phi2. Okay, so that concludes then this introduction to autoregressive models defined in a more general sense. What we will be doing next is we're going to be looking at moving average models in a general sense, and then after that we're going to combine this together to form our ARIMA models, and then ARIMA models mean autoregressive moving average models, and then eventually get to an ARIMA model, autoregressive integrated moving average model. So we're going to take this step by step and look through some derivations, look at the tools that R gives us to help us understand these models. Then eventually we will apply these to actual real-life time series data sets, and we'll look at these characteristics for our corresponding models that we've done the derivations for and try to match it up with what the data is showing us as well to make a judgment about what model should I use.